So, we know that now because we had this equation and now we have another expression for B. B can be represented as the curl of A, and that is why we can insert this here. If we insert it, then what I get here is that it is going to be dt then A, and which is because this is a space dependent operator, one can easily write down, one can take it out and one can easily write down like this way. Or in other words, we can combine these two, we can rewrite this as this cross product of E plus time derivative of the vector potential equals 0. One can write it down. So, if we can write down, here is another interesting property is showing up, and we are going to make use of that property of vector algebra. We are not proving that properties, how to prove that, I mean in a general form, but we will prove it here in terms of electric and magnetic field. So, what is the property we are going to make use of? Previously, we have made use of the property that if a function is divergenceless, then that function can be expressed, that vector can be expressed as a curl of another vector. Here, we are seeing that the curl itself is 0. This full quantity, the entire quantity, the curl of this entire quantity is 0. And the moment curl of an entire quantity is 0, which is a vectorial quantity is 0, it means that this curl of a gradient is always 0. Another vector identity, property of vector identity. So, what we are seeing is that because this part, this curl, I mean we know that cross product with the del operator is actually a curl. So, curl is 0, it means that this must be a gradient, must be a gradient of a scalar quantity. So, this E plus must be a gradient of a scalar quantity. This is just coming directly from the vector identities. There are many manipulations one can do. These are the consequences of vector identities. So, one can prove this immediately here. We will prove it here. If we take the let us say and gradient, which means that it has to be represented like this way, gradient of a scalar quantity. Phi is a scalar quantity. So, this is the scalar quantity we have defining. So, this part has to be represented, this E plus this entire part has to be represented. What we are noticing here is that we are just making use of pure mathematical concept to conclude something, and then we are trying to find out the physical meaning of it. We'll find out the physical meaning later. Right now, what we have shown that because this curl 0, and when the curl of a vector is 0, it means that this part is a gradient of a scalar quantity. So, this entire quantity is a vector quantity, but it is a gradient of the scalar quantity. So, and gradient is means it is the direction of change, which direction it is changing, that is the called gradient. That is the meaning of gradient. So, let us prove this, that it should be 0. If I have a curl of a gradient like this, then I can represent it like as usual. The curl can be represented as I, j, then k unit vectors, and then del x, and then I have gradient of this scalar quantity, which is nothing but this one, this is y, and this is z. So, this is the representation of the curl, and if I explicitly do that, simplify it, so it is going to be following. It is going to be now k del, this is y, this is y, this is z. Okay. Now, I have with respect to partial derivative with respect to y, and then partial derivative with respect to z minus j, partial derivative with respect to z, then partial derivative with respect to y. Then other two terms, these two terms will come in. Now, look at these terms. Here I have a dot product with between I and k and I and j, which means that the first term will be 0. Similarly, second term will be 0 and third term will be 0. So, entire term will be 0. So, we have proved that curl of a gradient is going to be is going to be 0. So, mathematically we are correct if we express it like this way. And the moment I express it like this way, that this entire quantity, that is the electric field plus time derivative of the vector potential, this entire thing is represented by the gradient of a scalar quantity. This phi is called scalar potential. That's the definition of scalar potential is coming in. So, I have the scalar potential formulation, which is nothing but E plus is nothing but this gradient of the scalar potential. So, gradient of the scalar potential is represented by this vectorial quantity. So, what we get in the end, but at the same time we should remember that we have to be correct with the sign, because here there should be one negative sign. Here there should be a negative sign. This negative sign, why this negative sign is coming up, we will understand it phenomenologically. This negative sign is coming up because this entire part is a vector which is some kind of a field, total field, let us say total electric field. Why total electric field? Because this is electric field and I am adding another quantity. If I am adding two dissimilar quantities cannot be added. So, if this is electric field, this has to represent some kind of electric field which is originating from the vector potential, but it is electric field. So, two electric fields are combined together. So, it is a total electric field. Now, total electric field, field is a force, and the total electric field depends on the gradient of the potential, but it is a negative gradient of the potential. Why negative gradient of the potential? We know that if the potential is increasing this way, then the force or the field will be acting along this way. That is the way they work. They are acting in opposite direction always. So, because they are acting in opposite direction, we have to put this negative sign. So, it is notationally we should be correct for this for this representation. So, the basic idea of this negative sign is coming from the fact that the total electric field experienced by the particle, the field is the force and force is acting along this direction, because if the charged particle is left here without any force, then it will just reduce its potential this way, and that's the way force is acting. But this way potential is increasing. This is the direction potential is increasing. So this opposite directionality of the potential versus field is pointing out that we should have a negative sign. So negative gradient should be there, and it doesn't hurt the mathematics as well, because as long as this part is valid, even if it is negative, it's still 0. So this part is still I'm okay with the Maxwell's equations. I'm not violating Maxwell's equation, but I have introduced this negative sign so that I am phenomenologically correct to make the two fields in the field and potentials to be opposite in direction. So in the end, what I get is that the electric field can be represented like this way. We have seen the magnetic field will be represented in terms of vector potential. So magnetic field can be represented in terms of vector potential. Electric field now can be represented in terms of vector potential and scalar potential. Both are contributing to the electric field. So there are two important realizations we have already got. When I have a medium and through the medium light is propagating through the medium. For the medium I have vacuum. I have selected vacuum to make things simple, and when it's going through it, light is going through this medium, then to describe the nature of the light I have to find out electric and magnetic fields in the medium, that is E field and B field. Specifically we are saying B field instead of H field, and we have to find out what is the nature of these fields, and we have seen that there is a particular way it's behaving. It's divergence-less, it curl exists, and time varying one field is generating the other field. That's the way we have seen already. But then we would like to convert it to the potential formulation. The moment we get the potential formulation, it gives you the origin of those fields in the medium due to propagation of the light. Now the origin is following. What we see that the B field, this is the magnetic field. Magnetic field originates from the vector potential. So magnetic field originates from vector potential, and electric field in this medium originates from scalar potential plus vector potential. So these are the two realizations we have, and we have to use that. Now what is the pictorial representation? We have said that in the first step mathematical derivation of potential formulation of Maxwell's equations, A is proposed to be an unknown function. We said that A is an unknown function, and later we said that it is the vector potential. So how does it look like now? Electric field, one can say that the electric field is the force. Force is acting to reduce the potential, electric field. On the other hand, the scalar potential is increasing in the opposite direction of the field. So this is the pictorial representation of the scalar potential, very naive pictorial representation of the scalar potential. So, scalar potential is increasing in a particular direction, and the field, electric field, total electric field would be acting in opposite direction. On the other hand, the pictorial representation of the vector potential is following. Vector potential A is rotating in nature like this way. So this rotation, rotating field, this rotating potential field basically is originating the giving birth to the vector field, which is perpendicular direction because it should follow the right hand rule. So if rotating like this way, then it should point along this direction. So that's the way one can imagine how these fields are correlated with corresponding potential. Scalar potential is easy to understand, easy to visualize. This is something gravitational potential. Let's say as we go up, gravitational potential is increasing, but at the same time force is increasing, but gravitational potential is in an opposite direction. So something like that. It is actually trying to reduce the potential. On the other hand, this vector potential, because it's a vectorial quantity, it takes some time to understand what is the meaning of it. Now, A is unknown function. We have said that A is unknown function, and one may, because A is an unknown function, one may conveniently impose additional condition to define it, because if something is unknown, we have to figure it out what is that unknown, and when we have to figure out what is unknown, we can impose many other constraints and then figure out what is that unknown. So that's the basic idea. So because A is an unknown function, one can conveniently impose additional condition to define it, and technically when we do that, it is called choosing a gauge to define this A. And selecting additional condition. Selecting additional condition for A. That is called selecting a gauge. Two commonly used gauges include Coulomb gauge. We very frequently use these two gauges. Coulomb gauge. Another gauge is Lorentz gauge. These are the two gauges we use very frequently. And what is the difference between these two gauges? It is just the defining conditions are different. Defining condition. So what kind of A it should be, we are just defining it, and then because it is unknown, we have to look for that with that condition. When the problems associated with light matter interactions are solved using different gauges, each gauge may render different mathematical derivation steps with varied difficulty levels. However, ideally they should not change the final outcome. That's the point. So even if we use a particular additional condition for A to define A, before we start describing the light atom interaction, the final outcome should be the same, ideally. Therefore, selecting a suitable gauge for a given problem of light matter interaction or light atom interaction is mostly our discretion. It is our freedom to decide what should be selected for a particular situation. If a particular gauge or particular additional defining condition is helping me get a simplified mathematical derivation, so we should follow that. So that's the basic idea. In the in our discussion, we will use this Coulomb gauge because that is easy to perceive, and when I say Coulomb gauge, it means that I will assume that this unknown function is divergenceless. It is purely rotating in nature, and this is the condition, additional condition we are imposing, and then we have to find out what kind of A it is going to be if I have this condition. If I have this condition. So if it is divergenceless, it is purely rotating in nature, and that is why we have shown this figure. It is purely rotating in nature, and that is the and curl, which is represented by the B field. Curl of A is going to be B field, and that's the way it's representing. So in every point we have in this vacuum, every point we have a vector potential field, rotating vector potential field, and the magnetic field would be just perpendicular to that to the plane of this vector potential field. So this is the meaning of vector potential, and additional condition we will use this one for getting the solution of light atom interaction. We will stop here, and we will continue this module in the next session.